So today I'm solving this problem GFG POTD problem of the day, where the problem is a BST, and we have been asked to calculate the precedor and successor of a BST. First, let me tell you what is a precedor or a successor. For example, we have this binary tree 50, 30, 70. You can see this binary tree. If my key is 65, then it is given precedor is the value that is lesser than 65, but it should be just 60, just near to 65. Suppose if I see this tree and calculate the in order, suppose I calculate the in order, BST, the in order of a BST is always a sorted value. So its in order will be 20, 30, 40, 50, 60, 70, 80. So it will be the in order value. I don't know whether it works here or not. Yes. So this is the in order value. This is the in order value of our BST, and the property in BST, that the in order of a BST is always sorted list. So if I need to calculate for key equals 65, what is the precedor and what is the successor? So precedor value will be the value just lesser than 65, but you can say 50 is lesser than 65, but I want the value which is very near to 65. So precedor will be 60, which is lesser than 65 but very near to 65. So precedor will be 60. Then let us go to the successor and we calculate the successor value. Successor is the value that is greater than 65, but just near to 65. So here the successor value is 70. It cannot be 80 because 80, the difference is very big. If you calculate the absolute value of 70 minus 65, it will be 5, but 80 minus 65 will be 15. So it's a bigger value. So we want a value which is very near to 65, but it's bigger than 65. So if we'll go to a next binary tree, this is my another binary tree. This is the tree. I want a value that is greater than 8. That is greater than 8. So which value is there that is greater than 8? It is 9. So in order successor is 9. It cannot be 10 because 10 is a very bigger value. Just greater than 8. That will be 9. And what about precedor? The value which is lesser than 8, but it's very near to 8. So which value is it? Uh, if I go to 8 and try to move left, because in BST, if we are suppose we are at 8 and we want to go to a very low value, then we have to go to left. Then we will travel. Suppose I'm sitting on 8 and waiting for a lesser value than 8. Then I have to go to left. Okay, I reach 1. Now can 1 be my precedor? It can be, but let's try for a bigger value. So can we go, if we want to go for a bigger value, shall I go left or right? In BST, right value is a bigger value. So let me go to right. So it is 4. So 4 can be also a possible precedor, or it can be greater than 4 also, right? Which is very near to it. So let me try to go right, but there is no value in the right. So 4 is my precedor. So let us discuss the approach first. I will not write the code for the most. Let me erase this code and reset it again. Let us not write the code. Let us first discuss the brute force approach. What can be the brute force approach? Brute force approach can be, we can calculate the in order value. Suppose I am taking a vector. And you know how to calculate an in order in a binary tree. It's very simple, like three-step process is there. If I need to calculate in order, then if I have a DFS function, suppose anything void DFS, I am not going to write everything here. uh, First step is, if root is, I'm not going to write like it's, if root is null, then you need to return. Then in order, we follow like this: left, root, and right. So let us go to left. Then this is my value. Then I have to go to right. So in this way, we will be able to store all those values. Suppose I take a vector v, I can push all my nodes, in order nodes, like of this tree, in a vector, and that vector can consist of all the that vector can contain this in order value. Now next thing for me, this vector will, suppose I'm talking about this test case. Let's talk about the about test case. It's very easy. For this vector v, it will consist of 20. It is not containing values, it is containing node, like exact node addresses: 20, 30, then 40, then 50, then 60, then 70, then 80. Okay, so I have to, this is a sorted array kind of. It's kind of, I can iterate also, and I can apply binary search also. That we, there's an approach called binary search, or we can do linear search also. Suppose I have to see for 65, so I want a value which is lesser than 65, so I will go to 20. It can be a possibility. 30 can be a possibility, I will store it. 40 can be a possibility, so new possibility is 40. 50 can also be a possibility. 60 can also be a possibility of my preceder. But when I go to 70, 70 cannot be a possibility because it is greater than preceder. So I just return that 60s, I just return that value. That 60 is my preceder. Similarly, for the successor, I can go from right to left and can say 80, it can be my successor. Okay, 70 can be my successor. Okay, can 60 be my successor? No. So at the end, I am returning 70. So I have both the values 60 as well as 70. 60 is my precedor, 70 is my successor. Okay. So this approach, if you calculate the time complexity, will be O of n. Space complexity will be O of n, because I am taking an extra space of this vector, this auxiliary space O of n. So we can improve on that. So let us try to do one thing. This first brute force was solved considering a observation that if we look at the in order, and lot of problems are there on BST, binary search tree, which are solved just based upon this property that for a BST, its in order will always be a sorted array. So let us try to look for a better approach where we don't need to take an extra auxiliary space. So one thing we can like this is a very general observation I am making. As we talked earlier, we have to find a value which is lesser than 65. Let us first only focus on preceder. Same approach I will go into implement, and same copy paste I will do in successor also. So let us try to find the value of preceder for the key 65. So let us sit on the root node. I am sitting here on the root node, and I want a value which is lesser than. So 50 can be a possibility, right? Yes, okay. 50 can be the possibility. So my preceder will be right now node 50. I am writing node 50 means a node which contains the address of this which has a value 50. Okay. Do I want a lesser value or a bigger value? I want a bigger value. Why do I want a bigger value? Because I want a value which is very near to 65. Okay. For a bigger value in a binary search tree, do I need to go left or do I need to go right? Okay. Can I use it? No. Leave it. So let us focus back. So 50 is our procedure value. So for a bigger value, because I want a value that is very near to 65, do I need to go left or right? I need to go right because at the right there's a bigger value. Okay. So I'm sitting on 70. But can 70 be my possible procedure? No, it cannot be. I have taken a very bigger value. So 70 cannot be my possible answer. Okay. So right now I'm sitting on 70, that is fine. But I have not replaced my procedure value. Procedure is still 50 because procedure means a value that is lower than the that is lesser than the key value. Okay. So I'm currently my current node is here and currently sitting on 70 and I think it's a very bigger value. So I will go right or left. 70 is a very bigger value. I have exceeded 65. So I will go left. Okay. If I go left and now I am sitting on 60, which is a lesser value than 60, which is a lesser value than 65. So my procedure can be replaced with 50. So this is my 60. Okay. Now I am sitting on 60. I want a value which is very near to 65. So shall I go left or shall I go right? So I need to increase my value from 60. Okay. In order to increase, I need to go right. But there is no value in the right of 60. So this is the result. So just this whatever I was talking, let me write the code for that. Node pre initially I will take it as null and I will first sit on this node 50 here. Suppose let me take this value as a current node which is a root, and you know how to iterate on a binary search tree while current, because till the time my current is not reaching to null I will try to find the value. If val is current dot val, no it is not val, it is, if you see here the class, it is data. Okay. If my val, for this test case for 50, if my val is lesser than 65, that is lesser than key, then what happens, I need to store pre. So pre will be current, and I will, where will I go, left or right? I want a bigger value, so I will be going right. Current dot right. Otherwise otherwise it means I got a bigger value. So suppose in place of 50, suppose there is 85, so I had to go left. So it will be current equals current left. So now I have calculated the procedure value. So I will write pre, that is a procedure value. Now I need to calculate the successor for 65. Same methodology I will apply. I will sit on 50 and I want a bigger value. So for the bigger value, I will go to right and store it. Same analogy I will use. So pre will be, it will be a successor. Again my current will be root. Again I will write a for loop, but this time, sorry, but this time there are some modifications. What is the modification? If val is greater than key, then I am storing and going to left. Otherwise, I'm going to right. Very simple, just opposite. At the end, I have both the preceder as well as successor. So I'm returning this in a vector. This is preceder. Okay, okay. So this is successor. Let me try to compile it again and submit. So it was a very simple problem based upon binary search tree and just based upon a property that in a binary search tree, if I am at a particular value at a particular node, I want a bigger value, then I have to go to right. If I am on a if I want a lesser value, then I have to go to left. That's it.